Okay, let us slowly get started. So, hello everyone, welcome to the week 2 problem solving session for the pattern recognition and application course. I am Tanuka Bhattacharjee. I am a PhD student in the electrical engineering department at IISc. So, as you saw in the last week, in these sessions we will basically be solving some problems related to this week's lectures. So, today we will focus on certain classifiers, mainly base classifier, minimum risk classifier. We will try to solve some problems, design some of those classifiers. Okay. So, let us get started. So, first we have some general questions about classifier. The first problem says, for a 2-class problem, the design surface is shown in figure here. Then which of the following could be the best classifier design? So, as you can see here, the feature vector that we are talking about is 2-dimensional. So, we have two different features, x1 and x2, and we have two classes, omega 1 and omega 2. So, for each object or each pattern, we have computed these x1 and x2 features. So, when we plot in this x1 x2 space, each pattern will be a point. So, all the points belonging to omega 1 are on the left side of this parabolic line, and omega 2 are on the other side, the right side. And this parabolic line that here we are showing is basically the decision boundary. So, one side of this is one class and the other side is the other class. So, the question is, what type of classifier is best suited for this? That is, basically the classifier will try to model this decision boundary. So, what type of classifier will be best able to model this type of boundary? So, since we can see this is a parabolic sort of boundary, which is a quadratic, which can be represented by quadratic equations, as we know. So, we can say that the quadratic classifiers will be the best suited for this, because the decision boundary here is a quadratic, can be represented by a quadratic equation. So, the quadratic classifier is the best suited for this particular problem. Now, let us say we have the decision boundary like this. So, here you can see that the decision boundary is piecewise linear. So, each short segment here is a straight line, and you have concatenated of different small straight lines like that. So, it is piecewise linear, each piece is a straight line. So, if we want to use a complete linear classifier, that won't be a good fit for this. Also, this is not, the boundary cannot be expressed by any quadratic equation. So, quadratic classifier is also not suited for this, but MLP classifier will be a good fit. As you know, MLP, each perceptron in a MLP can model one piece of these linear segments. So, since we have multiple perceptrons in MLP network, that might be able to model a piecewise linear boundary like this. So, for this particular boundary, this particular type of boundary, which is piecewise linear, we will be among the choices given, MLP will be the best suited one to go with. Now, if the class boundary is like this, so all the dark blue portions are from one class and the light portions are from the other class. Okay, so this is omega 1 portion and this is omega 1 portion, and this one is omega 2 portion. So we have to divide these two. We have to classify patterns belonging to these two classes. So here, as you can see, you can chunk these patterns into boxes, or in higher dimensional space, hyper boxes, and each box has a class belongingness. So this box belongs to omega 1 class, this also belongs to omega 1 class. Similarly, you can have a box over here, and all the points within this belong to class omega 2. So you can create or you can form a number of such boxes or hyper boxes in the feature space, where each box belongs to a particular class. So here you have two classes, so some of the boxes will be belonging to class omega 1 and the remaining will be belonging to class omega 2. If your feature is organized like that, so that you can form such collection of boxes each belonging to one particular class, then the best classifier for this type of feature distribution will be hyperbox classifier. So for this particular type of decision boundary or decision surface, we will be using a hyperbox classifier. Now the one option that remains after this is linear classifier. We have seen how the decision boundary should be for quadratic classifier, how it should be for MLP classifier, and how it should be for hyperbox classifier. So the other one is linear classifier. So basically, when you have a linearly separable class, that is, you can draw a straight line which will separate the two classes, then linear classifier is the best suited for this. That is, if your x1, x2 are your feature and omega 1 and omega 2 are the two classes you have, let's say your decision boundary is like this. Decision surface is, if you are going for higher dimensional spaces, 3D, then it will be a plane, if the decision boundary is a plane. Or if you are going to even higher dimension, if it is a hyperplane, then you will go for linear classifier, because all these type of boundaries like the straight line or a plane or a hyperplane can be represented by linear equations. So the linear classifier will be the best suited for this type of decision boundary. Okay. So these were some basic idea about when you will go for designing any classifier. You first see the data distribution and what classifier you will try out. So these problems will give you some idea about this. Now let us move on to the next problem. Here it is said that for a two-class problem, which of the following corresponds to Bayes classifier? So before I tell the answer, will any of you want to try which will be the answer for this? Ashwin is saying all are correct. Ashwin, if you see the options 1, yeah, right, except 2, 1 and 3, right. Ayush is also correct. 1 and 3 both are correct for Bayes classifier. So Bayes classifier basically classifies to the class omega 1 if the posterior probability of class omega 1 given the feature is higher. Basically, it tries to reduce the probability of error, as it tries to minimize the probability of error, that is the Bayes classifier. So when you design a Bayes classifier, the error that you get, that is the minimum probability of error achievable. So that is achieved when you are classifying a pattern as belonging to class omega 1 if the posterior probability of omega 1 given the feature vector of that class X, that particular object X, is higher than the posterior probability of omega 2. So this is correct. And when you have the posterior probability equal of both classes, then it basically lies on the decision boundary. So both 1 and 3 are correct answers for this. So once we know that, let's look at this problem. So here for this is also a 2-class problem, and the posterior probability distributions P of omega 1 given x and P of omega 2 given x are shown in the figure. So both are kind of a Gaussian type of distribution, though omega 2 one is not exactly Gaussian, a similar type of distribution, but the mean is shifted for both of them. So this is the posterior distribution for the 2 classes given the feature vector x. Now we are given an unknown feature vector x1. So if we plot x1 on the feature axis, we see that x1 belongs here. Now we have to say, if we are using a Bayes classifier, what will be the classification result for x1. So as you can see, this is the posterior probability distribution for omega 1. So for x1, the posterior probability value is given here. So this is P omega 1 given x equal to x1. This is the posterior probability value. And for the class omega 2, this is the corresponding posterior probability value. This is probability of omega 2 given x equal to x2. So as you can see from the figure, the posterior probability of class omega 1 is higher than class omega 2 given the feature vector x1. So Bayes classifier, as we saw in the last equation, will classify the feature in the class omega 1. So x1 belongs to omega 1 as per Bayes classifier. And why? Because the posterior probability of class omega 1 given the feature vector x1 is higher than the posterior probability of omega 2. That's why this particular feature will belong to class omega 1, or a Bayes classifier will classify it to class omega 1. Now we also saw about another type of classifier, which is the minimum risk classifier, which is a more generalized version. So if we have a minimum risk classifier, then what is the classification rule? That we have to select the correct one. Which of the following corresponds to minimum risk classifier? So in minimum risk classifier, as the name suggests, we will try to minimize the risk involved. So in case of minimum risk classifier, we have a number of actions that we can take, and for given a particular feature vector, we will take that particular action for which the risk is minimum. So the first option is risk of alpha 1 given x is greater than risk of alpha 2 given x. Then you classify is at x belong to omega 1. So basically alpha 1 here is the action that you classify as omega 1, and alpha 2 is the action that you classify the feature as class omega 2. So when you have a risk of action alpha 1 higher than the risk of action alpha 2, then you will not obviously you will not go with the action alpha 1, or you will not classify x as belonging to class omega 1. So this is not correct. The next option is risk of alpha 1 given x is higher than risk of alpha 2 given x, and you classify x as omega 2. So this is the correct option for this. So you try to minimize the risk. Here your risk for taking the action alpha 2 is less than taking the other possible action alpha 1. So you go with the action alpha 2, and that action is you classify x as belonging to class omega 2. So this is the correct option. And lastly, if the risk is equal, then you can classify it to any class. Any class that will not make a difference. So if you have, I'll pause for 1 minute here. If you have any questions till this point, you can ask. Okay. I don't see any doubts. I assume that it's clear till now. So I'll move on to the next problem. So this is the next problem, problem 5. So here what we have is, let x be a discrete single dimensional feature. It is discrete single dimensional feature computed from objects belonging to two classes, C1 and C2. So we have two classes, and x is an element of 2, 4, 6 till 20. So x can take any even value from 2 to 20. In this range it can take any even value, and it is a single dimensional feature, and this feature has been computed from objects belonging to two different classes, C1 and C2. The class conditional probabilities for both classes are shown in figure. So here a blue histogram corresponds to class C1, and the orange one corresponds to class C2. So the blue one basically the class conditional probability, that is the probability of x given C1, and orange one is the probability of x given C2. So that is basically you take different objects from class C1 and you compute x for all of those objects and you plot the histogram. What you will get is basically the class conditional probability of x given class C1. And similarly, you take a number of objects from class C2, you compute the x value for all of those objects and you plot the histogram. The distribution that you will get is the class conditional probability for the class C2. Now it is said that during data collection we observed that 1000 out of 5000 objects belong to class C1 and the rest belong to C2. Given these information, first we have to determine the prior probabilities, probability of C1 and probability of C2. So the prior probability basically means that the probability of that particular class in the prior data, the data that already you have, what is the probability of this particular class in that data. So basically that is based on the prior knowledge. The prior data you have is your prior knowledge, and based on that prior knowledge, what is the probability of each class. So this is simply a computation of probability. So probability of C1 or the prior probability of C1 will be given by, so we saw that we are given that during data collection we observed that 1000 objects belong to class 1 out of 5000. So the fraction that belongs to class C1 is 1000 by 5000, which is equal to 1 by 5. So this is the probability. So given 5000 objects, 1000 of them satisfies class C1. So the probability basically is 1000 by 5000, that is 1 by 5. So this is the prior probability of class C1. Similarly, the prior probability of class C2 will be, so if 1000 objects belong to class C1 and the rest belongs to class C2, then 4000 objects will belong to C2. So this will become 4000 by 5000, that is 4 by 5. So these are the prior probabilities of the two classes. Now you can see that we are assuming that there are only two classes. So, given an object, it will belong either in class 1 or in class C1 or class C2. So, you can see that since these two are the possible classes, the prior probability will add up to 1, and this is actually happening here. So, this is how you compute the prior probabilities of each class. So, this which is basically the fraction of data belonging to that particular class in your prior data set. Now, the next question is, this was question 1. The next question is, compute the posterior probabilities. Probability of C1 given x equal to 8 and probability of C2 given x equal to 8. So, first let us go with the posterior probability of class C1 given x equal to 8. So, you can write this as probability of x equal to 8 given C1 into probability of C1 by probability of x equal to 8. Okay. This is basically following the Bayes theorem. You can write the conditional probability as this. So, the numerator is basically the joint probability of C1 and x equal to 8, and denominator is the probability of x equal to 8. So, it gives the conditional probability of C1 given x equal to 8. Now, again according to Bayes theorem, you can compute x equal to 8 as, let me write the numerator first. So, in the denominator, the probability of x equal to 8, that you can compute as probability of x equal to 8 and Ci, and you sum it up over all possible I. So, this is basically the expansion. You can expand probability of x equal to 8 like this. So, if you take this joint probability of x equal to 8 and class Ci, and you take this joint probability over all classes, then the sum will be the probability of x equal to 8. And you can further express this joint probability as the conditional probability into prior probability of Ci. So, this is the expression that will that corresponds to the posterior probability of class C1 given x equal to 8. Now, from the graph you can see, if we consider the class conditional for C1. So, this term is basically the class conditional for C1 evaluated at x equal to 8. So, here we are given the class conditional for C1, the blue histogram, and here the bin that I marked with the tick, that corresponds to the x value of 8. So, here the value is 0.45, the probability is 0.45. So, 0.45 into probability of class C1, the prior probability of class C1. As we already computed, the prior probability of class C1 is 1 by 5. So, this into 1 by 5 divided by, first if I take I equal to 1, then this is the same term as the numerator, probability of x equal to 8 given C1 into probability of C1. So, it will be the same term plus, if I take I equals to 2, then we are basically considering the class conditional for class C2, which is this orange histogram. So, when x equal to 8, the value of this histogram is here, this is 0.05. So, it is 0.05 into class conditional of not class conditional, I am sorry, the prior probability of class C2, and we computed that as 4 by 5. So, this is the posterior probability of class C1 given x equal to 8. Now, can any of you compute and tell me the probability? So Siddharaj is saying 9 by 13. Yeah, you are correct. It's 9 by 13 or 0.69 you can say. So this is the posterior probability of class C1 given x equal to 8. Now the other part that we had was we have to compute the posterior probability of class C2 given x equal to 8. We can proceed similarly as this one. So we have to compute probability of class C2 given x equal to 8. So the expression we will have is probability of x equal to 8 given C2 into probability of C2 divided by summation probability of x equal to 8 given Ci into probability of Ci, where summation is over I equal to 1 and 2. So now first term, the probability of x equal to 8 given C2, this is basically the class conditional probability of x equal to 8 for the class C2. So the orange distribution, and for 8 we have 0.05. So this is 0.05 and the prior probability of C2 is 4 by 5 divided by, the denominator will be exactly same as the previous because that was also the same expression. So we will have 0.45 into 1 by 5 plus 0.05 into 4 by 5, right. So this will correspond to 0.31, approximately 0.31. So here also you can cross check like this, that given x equal to 8, you can either classify the object as belonging to class C1 or belonging to C2. So these are the possible options. So the probability of C1, the posterior probability of C1 and C2 given x equal to 8 should add up to 1. So here we have 0.31 which is the posterior probability of class C2, and earlier we had the posterior probability of class C1 as 0.69. So you can see that the sum is actually 1. So this way we can also cross check that indeed the posterior probabilities that we calculated is correct. This is the case because these are the only two possible choices, class C1 and C2. Either x equal to 8 will belong to class C1 or it will belong to class C2. So the probability of both should sum up to 1. I hope this is clear. Then I will move on to the next problem. Okay. So here we are given that we have to consider again our two class problem with the single dimensional feature space. Single dimensional feature space, let's say the feature is x again, and equal class prior probabilities. That means if omega 1 and omega 2 are the two classes that we are considering, then probability of omega 1 will be equal to probability of omega 2. That is we have equal prior probabilities of the two classes. So each class, both the classes are equally likely to happen. Now let the class conditional densities be normal with distinct mean and variance. That means if we write the class conditional for class C1, let's say so it will be a normal distribution with some mean and variance. Let's say we take the mean as mu1 and variance as sigma 1 for class C1, and since the mean and variance are distinct for the two classes distributions, class conditional densities, so we will take mu2 and C2 as the mean and standard deviation for class C2, and mu1 and sigma 1 are for class C1. So the class conditional density for class C1 will be, as we know, the normal distribution exponential of minus x minus mu 1 square by 2 sigma 1 square. So this is basically our normal distribution with mean mu 1 and standard deviation sigma 1. We all know this. So this is the class conditional density for class C1. Similarly, the class conditional density for class C2 will be 1 by root over 2 pi sigma 2 square exponential of minus x minus mu 2 whole square by 2 sigma 2 square. These are the two class conditional probabilities. So we know the prior probabilities, we know the class conditional probabilities. Also the loss function is given. So lambda 1 1 and lambda 2 2 is 0. That is, if you classify the object correctly. So if the object belongs to class C omega 1, or sorry, I jumbled up the notation a bit, I am really sorry. I will use omega 1 and omega 2 throughout. Yeah. So if the object actually belongs to class omega 1 and you have classified it at omega 1, so the loss is 0. Similarly, if it belongs to omega 2 and you classify it as omega 2, then the loss is 0. But if you do some misclassification, then the loss is non-zero. Then we will have to design the minimum risk classifier. Now how to do that? So as you know, the expression of risk is, let's say alpha is our actions, alpha I is the actions that we can take. Here we are considering two actions, alpha 1 and alpha 2. Alpha 1 means you are classifying the object as belonging to class omega 1 and alpha 2 means belonging to class omega 2. So for any action alpha I given the feature vector x, the risk is given by r of alpha I given x equal to summation lambda I j probability of omega j given x. Basically the expected loss. We are computing the expectation of the loss value. Lambda I j weighted with probability of omega j given x. And we will sum over j equal to 1 and 2. This is the general expression for risk. So the expression for risk of alpha 1 given x will be lambda 1 1 into probability of omega 1 given x plus lambda 1 2 into probability of omega 2 given x, right. So as it was mentioned in the question that lambda 1 1 and lambda 2 2 are 0 and lambda 1 2 and 2 1 are non-zero. So here lambda 1 1 is basically 0 and lambda 1 2 is greater than 0. So we will keep that as lambda 1 2 only. So our expression will become lambda 1 2 into probability of omega 2 given x. Okay. Similarly, we can compute the risk of alpha 2 given x as lambda 2 1 into probability of omega 1 given x plus lambda 2 2 into probability of omega 2 given x, following this general expression. Here also we know lambda 2 2, this one is basically 0 and lambda 2 1 is non-zero. So our expression will become lambda 2 1 into probability of omega 1 given x. So now we will go for the action alpha 1 if the risk of taking the action alpha 1 is less than the risk of taking the action alpha 2. That is, we will classify the object as x belongs to omega 1 if the risk of alpha 1 given x is less than the risk of alpha 2 given x. If we put the expressions, that means lambda 1 2 into probability of omega 2 given x should be less than lambda 2 1 into probability of omega 1 given x. If this condition is satisfied, then we will classify the pattern x to belong to omega 1. So, now let us simplify this expression a bit. So, what we have is lambda 1 2 into probability of omega 2 given x less than lambda 2 1 into probability of omega 1 given x. This probability of omega 2 given x and omega 1 given x, these are basically the posterior probabilities. So, as we know, we can express these posterior probabilities as the class conditionals and the prior probabilities. We can use class conditional and prior probability to express the posterior probability. So, the probability of omega 2 given x can be written as probability of x given omega 2 into probability of omega 2 divided by probability of x. That should be less than probability of x given omega 1 into probability of omega 1 given divided by probability of x. Now, since probability of x is a positive quantity, we can cancel this out for both. This will be equal also on both sides. So, we can cancel this out. So, this will be the expression. Now, again we were given that prior probability of the two classes are equal. So, probability of omega 2, this term and this term are basically equal because the class prior probabilities are equal. So, we can also cancel these out. So, the remaining expression that we have is lambda 1 2 into probability of x given omega 2, that is the class conditional of class omega 2, should be less than lambda 2 1 into probability of x given omega 1. If this is the case for the x for the feature vector x, then we will classify it as belonging to class omega 1. Now, let us put the expressions for this. So, as we said earlier, these two expressions are the normal distributions with different mean and variance. So, it will be like this. Again we can cancel the 2 pi, and if we take the log of this, let us take the log of this, since log is a monotonic increasing function, that will retain the relation as it is. So, if we take the log of this, let us say ln of this, then we have ln of lambda 1 2 by sigma 2. I am taking sigma 2 square out of the square root, minus x minus mu 2 square by 2 sigma 2 square should be less than ln of lambda 2 1 by sigma 1 minus x minus mu 1 square to sigma 1 square. Right. Now let's take all the x's on the left side, or let us take everything on the left side. We get this should be less than 0 to classify x as belonging to class omega 1. We can further simplify this expression. So we will have x square plus mu 1 square minus 2 mu 1 x minus 1 by 2 sigma 2 square x square plus mu 2 square minus, it will be minus 2 mu 2 x plus ln of, we have ln of lambda 1 2 by sigma 2 minus ln of lambda 2 1 by sigma 1. So we can combine it in one term. So it will become lambda 1 2 by sigma 2 into sigma 1 by lambda 2 1. This should be less than 0. Now if you take the x square terms or the quadratic terms together, you will get this, it is 1 by 2 x square into 1 by sigma 1 square minus 1 by sigma 2 square. Now we take together the terms with x. So we will get plus x into mu 2 by sigma 2 square minus mu 1 by sigma 1 square plus then the constant terms. So it will be half mu 1 square by sigma 1 square minus mu 2 square by sigma 2 square plus ln of lambda 1 2 by lambda 2 1 into sigma 1 by sigma 2. This should be less than 0, right? Right. So this is the final minimum risk classifier expression. So if x satisfies this equation, you take the action alpha 1, that is you classify that x is element of omega 1, and if it does not satisfy, you classify x to belong to class omega 2, that is you take the action alpha 2. So as you can see that the expression that you need to compute is a quadratic expression. So this is basically boiling down to a quadratic classifier. Now Now we have designed the minimum risk classifier. We have two more parts in the question. What will the classifier be if the two class conditionals have equal variance, unequal mean and lambda 1 2 equal to lambda 2 1. So it mean to say is sigma 1 equal to sigma 2 in our case. So equal variance means the standard deviation is also equal. Unequal mean, so we have mu 1 mu 2 two separate means and lambda 1 2 equal to lambda 2 1. Then what will be the classifier? So if you put those values over here, so variance is equal, so the first term becomes 0. So here let me write the condition. So here we have sigma 1 equal to sigma 2, mu 1 not equal to mu 2 and lambda 1 2 equal to lambda 2 1. So the first term boils down to 0. This one becomes 0. The second term will become, let's say sigma 1 equal to sigma 2 equal to, we take a common term sigma. So the second term will become x by sigma square into mu 2 minus mu 1 plus 1 by 2 sigma square mu 1 square minus mu 2 square plus, here sigma 1 sigma 2 are equal, again lambda 1 2 lambda 2 1 are equal. So the term within the log function is becoming 1, so ln of that will become 0. So we do not have the last term also. So this is the classifier we have for this case. We can further simplify this classifier. I will do it here. So if we further simplify this classifier, we can write x into mu 2 minus mu 1 should be less than half of mu 1 plus mu 2 into it should be mu 2 minus mu 1 because I have already changed the side. So it has, if I take the second term, this term to the right side, it will become mu 2 square minus mu 1 square. So if I factor it out, mu 1 plus mu 2 into mu 2 minus mu 1. So I am assuming that mu 2 is greater than mu 1 for the sake of simplicity. Then I can cancel these two terms out, assuming mu 2 is greater than mu 1, that is this term is positive. So your final classifier is becoming x is less than mu 1 plus mu 2 by 2. Then you will classify the object to belong to class omega 1. Okay. Now, so that is also intuitive, right? Because you have the same standard deviations of both the distributions, but the mean is similar. Mean is same. Mean is not same. You have same standard deviation, but the mean is different. So the intuition is you will put the decision boundary somewhere in the middle of the two means. So basically that is the case we are also getting here. Now the other part says, problem part 2 says the two class conditionals have 0 mean, unequal variance and lambda 1 2 equal to lambda 2 1. So here the condition that we are having is, this is the part 2, mu 1 equal to mu 2 equal to 0. So 0 mean, then unequal variance. So we have sigma 1 not equal to sigma 2, 2 separate, and lambda 1 2 equal to lambda 2 1. Then what will be the classifier be? So let us first take the general expression for the classifier. I will write it down once more. This was the expression for our general classifier. Now we are given that sigma 1 not equal to sigma 2, but mu 1 mu 2 are 0. So if we put that, the first term remains as it is. Second term will become 0 because both mu 1 mu 2 are 0. The third term will also become 0, and the fourth term will become ln of sigma 1 by sigma 2, because lambda 1 2 equal to lambda 2 1. This is less than 0. Then you take the action alpha 1. You can further simplify this. That will become, if you take x square, keep x square to the left and take everything else to the right, it will become ln of sigma 2 by sigma 1. If you take it on the other side, then you have sigma 1 square, sigma 2 square, 2 by sigma 2 square minus sigma 1 square. So if your x square is following this criteria or this inequality, it is satisfying this inequality, you will take the action as alpha 1, that is, you will classify x as belonging to class omega 1. Okay. Okay, so these were the problems for this session. If you have any doubts, we have 3 more minutes remaining for today's session. If you have any doubts, you can post it in the chat, or you can speak out. I'll stop here. Okay, so since we don't have much time today, I planned one more problem for the base classifier. I will take that up in the next class. That will actually take some time to explain. So I'll explain that in the next session. In the meantime, if you have any question from the problems we solved in this session today, you can post it. Okay, since we don't have any question in the chat box, I'll close this session. Thank you all for joining. We'll meet again in the next week with the next set of problems. Thank you.